So, how accurate do you need to be to know the difference between the end of the back end of one car and the front end of the one that's coming quickly behind it?
No, that's a good question. I mean, they're separated by about half a meter on the
Oh,
production.
right.
So at some level, you have to be kind of, accurate to that kind of level. The biggest challenge actually is not so much the instantaneous accuracy in a nice clean environment. It's actually dealing with the fact that as you're doing this, the tools are sometimes used in the wheel wells or under the car or in
Oh,
environments that are not ideal at all for propagation. I think people have their mobile phones give them a false sense of security about how radio signals propagate around the environment. They don't ever really see the fact that radio signals are blocked by all sorts of things. People, I mean, people are fantastic radio absorbers. Wet, salty, bodies are fantastic at just soaking up radio waves, as are bits of car, metal parts of car or metal parts of production transport systems or something like that. So in those environments, it actually you very rarely get really good propagation from beacons on tools or on cars into infrastructure that you place around the production line. You're always being challenged by reflections and obstructions and so on. So even if your technology works at 50 centimeters in a nice clean environment, the question is more what's the level of reliability and robustness you get when you're dumped into a hellish environment, and is it good enough to do it there with the levels of reliability that then people need? And it's a challenging problem. So
but presumably even ultra wideband is not going to propagate through sheet metal or someone's body, is it?
no, you're right, and I think that the important thing there is that actually you have to put up enough infrastructure that at some point you have a few near lines of sight, right? So if you go from line of sight to near line of sight, your accuracy of your system degrades. I mean, it's just kind
Hmm.
of just going to, right? If you go from near line of sight to no line of sight or blocked, then things get a lot worse, a lot more quickly. So a lot of these car production lines have to have enough sensors that you're getting the basic number of line of sight or near line of sight paths, even in those really challenging kind of situations. And then it's down to how much information do you squeeze out of every line of sight or near line of sight path that you're getting. So if you're, and this comes back down to location system architecture, really, right? So if your location system is a pure TDOA location system, you'll need four
So that's
near
time
line of
difference of
sight.
arrival, right?
Time difference of arrival, sorry, yes.
Yeah.
So if you've got a pure time difference of arrival system, like GPSs, or like, there are many radio time difference of arrival systems, then essentially you need four of those pretty clean or nearly clean paths to get your 3D location with any accuracy. If you do two-way ranging, so that's normally called TOA or time of arrival, where you're sending a signal out from a tag to an anchor and it comes back again and you measure the two-way trip, you might need three, right? So that's kind of a bit better and a bit more robust in those really challenging circumstances.
Hmm.
If you use AOA, actually you only need two.
Hmm.
So, that's an even more robust technology. And we actually use a combination of AOA plus TDOA. So that actually gives us a lot of information from any path that happens to kind of make it through the maze of the maze of obstructions that you're placed around.
Now that's interesting. So you're, and I always call these, if it's on an asset that's moving around, then I tend to call it a tag, and I try and
Yeah.
call beacons of things that don't move. But the complicated thing is that tags tend to use beaconing radio protocols, which just really confuses everyone. But anyway, let's get back to the point. This mixing of AOA and time of arrival. So so you're using both, and ultra wideband. With ultra wideband, is that the time of arrival, your time difference of
Well,
arrival,
actually,
or
we
time of
measure
arrival?
the ultra wideband does both. So you can measure an AOA on a ultra wideband signal in the same way that you do on, say, a BLE
Okay,
signal, right? So
all right.
that part of it's very, very similar. It's a bit easier because of the shorter signals to measure that TDOA on a ultra wideband signal than on a BLE signal. So we have the opportunity with ultra wideband to do both of those techniques at the same time, and they complement each other quite well. But essentially, what you're trying to do is you've got a direct path. Squeeze as much information out of it as you possibly can, because you may not get many more of them, right? So from a robustness point of view, it's a very robust technology, but it's probably it is a bit more expensive than BLE. So if you look at the kind of applications that you have in car plants, then BLE might be a great application for logistics store areas or something like that, where either you don't need quite the accuracy and or quite the robustness at the same time. It might be a great application for those. Whereas somewhere on the production line, it's a very nasty radio environment, and one needs to squeeze out as much information as possible with the highest bandwidth signal. So in my view, when we put together location systems, it's always horses for courses. You use the best technology for the particular problem that you're looking at. And I although we make ultra wideband sensors, there are applications where ultra wideband just isn't good enough. So we work with car manufacturers who want to do what's called bolt level accuracy, where if let's say you've got a good example is a helicopter is the rotor blade assembly for a helicopter. You have lots and lots of bolts, and they have to be bolted down in precisely the right sequence. You kind of imagine changing the wheel on your car, the tire on your car. You're supposed to kind of tighten the bolts on the wheel in a kind of if you tighten the one here first, then you go across the wheel to the next one, then back to the next one. So there's a particular way in which it's the best way of doing it. Well, for a helicopter plate assembly, it's like that, but there's 50 bolts, and the consequences of getting it wrong are really bad, and all of those bolts look alike. So there, you need to basically be able to tell within a couple of centimeters where the tool head is as you're assembling this thing, to make sure that the assembly process has happened exactly right. And that's beyond BLE or ultra wideband. In fact, probably the only way of doing it is optical. So for those kind of applications, we suggest optical techniques, because it's the only way of really being sure about what you're doing. So there's a continuum of location technologies, each of which is applicable to different industrial kind of applications.
And the optical, is that machine vision, or is it visual light communication, where you're what are you using?
It's a good question. We work with a company called ART out of Germany, and ART have built a tool mounted camera. So it's kind of like a little camera that looks directly at where the tool is being used on the assembly, and it looks at the area around the bolt to figure out which bolt you're looking at. So they actually originally did it for things like engine assembly in car production lines, right? Because if you imagine kind of trying to work on an engine, deep in an engine that's in the kind of engine bay of a car, and there's a metal hood above you, it's a really awful scenario for anything that's kind of outside the car, trying to detect signals that are coming from a beacon or something like that in. You can't look into the car, you can't get any signals out. The best you can do is actually look at what's happening inside the bonnet or inside the hood of the car, with a tool that's got a little camera on it. And the camera can see the area around the bolt, and it can see exactly where you are with respect to other bolts and so on. And actually, with a bit of machine learning and AI, they can tell exactly which bolt it is that you're looking at. And so you can then end up with some quite interesting combinations of technologies, because this ART vision-based technology is quite capable of telling you within an engine block, which individual bolt it's looking at. But one thing it doesn't know is which car you're looking at. So every car, the engine block looks identical to the ART system, but you can combine that with the tracking from ultra wideband or with BLE or something like that. On a production line, we combine it with ultra wideband, because the ultra wideband knows exactly which car the tool is working on right now, and the ART vision system knows exactly which bolt on some car it's working on right now. And if you combine those two things, you can essentially work out exactly which bolt you're working on any car in the factory, down to the individual bolt. And so you can do quality control processes and understand exactly what's happening at a much, much deeper level than you were ever able to do before. But that's only possible because you're using a combination of different technologies, each of which have some strengths and some weaknesses. But if you combine them in the right way, you can get a combination that's strong in both regards.
Thanks for watching this clip from the Mr. Beacon podcast here on YouTube. You can listen to the rest of this episode on iTunes, Spotify, or wherever you get your podcasts. If you enjoyed it, please like and share this video, and be sure to subscribe for more weekly videos. For more information about Wiliot and IoT Pixels, head on over to wiliot.com.